Yeah, so I guess we're on the half hour now when we're supposed to start. So thanks everyone for joining today's session. My name is Anders Jönsson. I'm a sales specialist for the cloud infrastructure and automation team here at Conscia Sweden. Today's session will be focused on, essentially a demo session of Portworx. We're going to talk a little bit about what Portworx is and the architecture around it, and essentially have a bit of a focus on how to handle VM storage in an OpenShift environment, since we've seen quite a big of a market shift asking for alternatives to what customers may be using for virtualization today. So this is a way to show an alternative on how this can be handled and to have a stable and secure data handling of that solution as well. With me today I have Eric from the Portworx organization, a part of Pure Storage, and he will take us through this demo and hold our hand throughout the day. Before I hand over to you, Eric, please, if you have any questions, you can post them in the Q&A or chat session here, and it will be recorded so you can receive this afterwards and share it with friends and colleagues, of course. And at the very end we will have a Q&A session and try to go over these questions if we don't prefer to do them on the fly, Eric. So over to you. Thank you.
Sure, thanks, and good morning. Today's first session around modern virtualization. We call it modern virtualization because basically virtualization has been around for a long time, but what we're seeing now is a move that lots of customers are moving towards virtualization inside container platforms. And that's why we call it modern virtualization, which is similar to modern apps, if you will, or virtualization 2.0. So my name is Erik Sandboer. I'm a cloud native architect for Portworx, covering the EMEA North region, and this is today's agenda. So first we're going to talk around why persistency and why Portworx for persistency. We're going to spend some time looking at the Portworx architecture. So how is this thing constructed? Then we have some bits and pieces, and I can see that the agenda is mixed because first we'll be running the demo, or the first part of the demo in that case. Then as the demo progresses in the background, because there's one piece of the demo that takes a significant amount of time, then we'll dive into disaster recovery for VMs in OpenShift with Portworx. And finally, we are going to briefly revisit the lab and see whether what we started, if it actually worked. And then we're coming to a close with some Q&A. Of course, those will be the questions that we gathered up during the session. And if there's like a bit of a silence as we're doing things inside the demo, then maybe I'll just ask the presenters from the co-presenters from Conscia whether there are any questions so far, and we may be able to do some questions in a bit more flexible way. So starting out with persistency. So right, persistent storage. This is a bit of a flashback, right? Spinning drives. We do still support them. We don't see them very much. The big question is, why would you have persistent storage, especially inside containers? So please consider the most boring application that I know, right? So this is Notepad. It's got to be the most boring application ever. Still, there's this checkbox that says work wrap. And what happens if you close Notepad and open it again? Checkbox is still there. So the most boring application that I know is actually a stateful application, which also means anything more interesting has got to be stateful at some point as well. Now, when you convert this into the world of containers, containers can be stateless. In fact, when you look at cloud native, when you type up 12factors.net, so the 12 factors that will make you the perfect and most awesome cloud cloud native application, one of the points it says is that the application is ran as a number of processes that are stateless. So originally the idea was, let's not have a state. It's really easy because if a pod or a container, if it dies, you can just restart it because it's stateless anyway. So it will be very easy to recover. So nowadays we're starting to see more and more that people actually do want persistency inside containers. People are starting to run databases inside containers, very often even following the Kubernetes way of doing things, if you will. So everything is scale out. So there's now scale out databases. Of course, they need to have a state, right? If the application should die or be restarted, the storage should still be there. So for containers, that is something that's developing. But for virtual machines, it's a given, right? How else would you boot the operating system inside a VM? You always need persistent storage. And you don't just need persistent storage, you also need performant persistent storage, because usually, or I should say often, the performance of a virtual machine is measured by the latency to the disk. So it is very important that you have like a decent solution. So Kubernetes in the early days quickly discovered that, hey, even though we designed this container orchestrator as running stateless workloads, we might have to support statefulness. So very early on, they built what we call the in-tree volume drivers. So they started out with local disk. So being able to grab a local disk from server and surface that up into a container, which of course doesn't make a lot of sense, because if that worker node was to die, which in the world of Kubernetes is no big thing, right? Because we would replace it with a new one, but you would have just lost your storage. So pretty soon followed iSCSI, NFS, Fiber Channel, all generic drivers, where you would manually feed Kubernetes with a Fiber Channel connected something, and then pass that through into the container. But that is all static, it's clumsy. So at that point, all of the storage vendors and everyone who was doing a little bit of something inside Kubernetes, like dove onto it and said, we want our own in-tree volume driver, up to a point that it was unsustainable. And for the record, even Portworx was in there at that time, right? Because Portworx was, well, actually it was a product before Kubernetes. So we used to support things like Mesosphere and Docker Swarm. Nowadays, everything is turned into Kubernetes. So today we support Kubernetes, no longer with the in-tree volume driver, because they were all deprecated, or almost all of them, in favor of this thing, the container storage interface. So the CSI is basically a framework inside Kubernetes where storage vendors can hook their own code into, and that actually freed up a lot of stuff in Kubernetes. So the Kubernetes developers were like, this is way better, because now we're not getting slowed down with all these in-tree volume drivers that we can't even test. So now it's just the CSI framework, and it's up to the vendors to build a solution. So as a result, all of the storage vendors dove onto CSI. And basically, this is what they came up with. So you have Kubernetes, you have a storage array, you install your CSI driver specific to that storage array. And now, if you, from a Kubernetes perspective, want to deploy storage, the CSI driver springs to life, talks down to the array through an API. It will carve out a LUN, for example, and it will surface that, and it will then surface that LUN up into Kubernetes. And it's done. Really easy way to get storage into Kubernetes. So it seems that this would solve all of your problems, right? Because now I can carve out LUNs, I can surface them up as PVs. It's a done deal. Or is it? Because Kubernetes isn't really storage aware. It was never actually designed to be storage aware. So there are some questions. How do you solve things like replication? DR failover. So anything that lives in this Kubernetes cluster, how do you replicate that somewhere else? You could do it for the storage. You could replicate the storage using the features inside the storage array, but then you'd have all of your persistent volumes in some other Kubernetes environment without actually having all of the Kubernetes objects in the other environment. So Another thing is resiliency. If a worker fails that has this this storage connected, chances are, even if Kubernetes decides to start it elsewhere, that the storage array won't be able to connect that LUN into the new worker node because it's still connected to the old and half failing one. So resiliency can also be an issue. Then next you get things like app mobility. How do I move workloads? It's really easy in Kubernetes until you have persistent storage attached, because now you need to move the storage as well. And many other things, role-based access, multi-tenancy. Lots of arrays were never meant to be multi-tenant. So how do you add that to this world? Scaling is also an issue, because right here I have one LUN connecting into one PV, so one persistent volume inside a container. Imagine if you're familiar with VMware, for example, imagine that would be the way it worked in VMware. You would have one LUN for each virtual disk. So before you know it, you'd have, like, in a larger environment, you'd get like 30,000 LUNs just for all the virtual drives, right? There's no abstraction in between in this scenario. And for Kubernetes, it's even worse, because if you have 1,000 virtual machines that run monolithic applications in the world of cloud native, that would probably translate into like 10,000 or 30,000 containers, which use even more smaller PVCs, meaning even more LUNs. And it's generally not possible to like drive like 80,000 LUNs from a storage array. So, vendors starting building out all kinds of stuff into Kubernetes to actually make it work and basically solve all of these issues. But really, I think we need to look beyond CSI. So look a bit further. And of course, the first question is, why is there an aircraft in this picture? Well, so this is a Harrier jump jet. It's all about doing things differently. So I saw a documentary once, and one of the test pilots of this plane said, it's much better to stop and land compared to land and try and stop. So this is all about vertical takeoff capabilities that this aircraft brought to the scene. It's different, right? It's a different approach to a common problem. And that's exactly what Portworx is doing as well. We're doing things, but basically turning things upside down. When you look at what we provide, yes, we still do the default stuff. So Portworx CSI is still a thing when you connect it to the main company Pure Storage. So you take a Pure Storage array. We have a CSI driver that, just like most competition, does the same thing, right? We have an array underneath. We will surface up volumes through CSI into Kubernetes. But the interesting part is the other side of the coin. That's Portworx Enterprise. That is turning the world upside down. So what we're doing in Portworx Enterprise has a completely different architecture, as you can see here. So this is what we already talked about, right? This is a standard CSI connector approach. So there's a LUN on a storage array, and it translates directly up through the CSI driver into a PV on Kubernetes. What Portworx Enterprise does is it builds a storage layer that lives inside Kubernetes. So instead of having a storage layer in the storage array, using all of that data services from the storage array, we've turned it around. We are now saying, hey, let's build a software-defined storage layer inside Kubernetes, and then go down to the storage array, or go down to local disk, or go down to cloud storage, basically any block device, in order to use that to construct a pool of storage, and then we carve PVs out of there. So you can see that it's architecturally different. And yes, we're still using a CSI driver, because that's the way Kubernetes interacts with storage. The only difference is we don't use the CSI driver to go down to a storage array, but we use it to go down to our software-defined storage. And you can see that in this case, it's also been abstracted away. There's a couple of large LUNs or block devices that you add into Portworx. It will build that out into a storage pool, and then it can carve tens of thousands PVCs out of the storage pool, while only using a few LUNs on like the south side of Portworx. So this is very much the way that VMware solved the problem as well, right? You feed it with a couple of LUNs, it builds into data stores, then VMware carves out many virtual disks out of those data stores. Well, this architecture in that respect is similar, because here too, we have like only a few larger block devices. We built that into a storage pool, and then we can carve out tens of thousands PVs out of that. So when you use this construct, you're building a storage array inside Kubernetes. It becomes really cool because now you can run any application, whether that's a container or a modern virtual machine, as we'll see later. You can run it on any Kubernetes distribution, and in this example, we'll be using OpenShift. It can run on any cloud because Kubernetes is Kubernetes, right? Once you can run in Kubernetes, you can also run in AKS, EKS. You can deploy Arrow. You can deploy the AWS equivalent of Arrow. So basically getting OpenShift inside public cloud. You can run it on any infrastructure, right? You can run it locally. You can have it backed by any vendor storage array, any local disk, or of course any cloud drive inside public cloud. As long as it's a block device, we can use it. And you can use it for any stage as well. So when you translate that into the OpenShift case, this is what you want to do. You want to run all of your applications. And in case you're using OpenShift, you can use OpenShift virtualization to run it as VMs or containers or combined, as we'll see in the lab later. It runs on infrastructure, whether that is cloud infrastructure or your own infrastructure. And then, of course, you have the modernization piece. So yes, you can run VMs, you can run containers, you can even migrate workloads that live inside containers, inside VMs into straight containers if you wanted to. So that is all that the Red Hat OpenShift platform will give you. But when you add Portworx as a storage layer on top of that, you can now imagine that you can run that on any infrastructure, right? Whether that's on an enterprise SAN, whether that is hyper-converged, whether you want to run it in public cloud, maybe you want to do things like DR between public cloud and on-premise, or DR between two public clouds, or DR between two on-premise locations. You can do basically anything you want once you have built it out, you've built out this stack. So how does Portworx work in detail? It's built around several products. The one on the bottom, PX Store, that is basically the software-defined storage. Then we have other features, like we have PX Backup, if you want to perform backups of the environment. We have PX DR, which will take care of DR scenarios for you. We have Autopilot that allows you to auto-scale. So as you fill up things, Autopilot will automatically grow it. So that's the part of the demo that actually will take time. So we're going to start that off and then continue later, see what happened. PX Migrate, if you want to migrate workloads from one cluster to the other, or maybe even between namespaces within the same cluster. PX Secure will deliver you encryption, things like role-based access, multi-tenancy. And basically, that covers the entire Portworx enterprise portfolio. Now, the architecture is something like this. So here we have like the minimum of a 3-node setup. We deploy Portworx on all of the worker nodes. The worker nodes can use SAN, they can use cloud drives, they can use SSDs, they can even use HDDs if you wanted to. It will all grab them together, build them into a pool or several pools, so that depending on the performance, it can build several pools. So it will auto detect an HDD from an SSD, for example, and say, hey, this is a slower pool, this is a faster pool. And basically, then it will serve that out as shared storage. So how does that work? Well, first you install Portworx using an operator. So it's a level 5 operator, which means it covers day 0, 1, and 2. And after you've deployed it, you can start deploying your workloads. So here you see an example of 4 worker nodes, 5 worker nodes actually, and 4 of them contain storage. So whether that's an SSD or it's a LUN, so something coming from a storage array underneath, it will grab all of that storage and build it into a storage pool. Now, as you can see, there's one worker without storage. We'll see what that's about. So if I deploy an application and I use REPL1 or a replication factor of 1, obviously we get one copy. So we have one copy, it's placed on one of the devices down here, and it works. But if you lost this worker node, you'd lose the data. So you might go up into REPL2 or a replication factor of 2. What it will do now, so Portworx will take care of the replication, and it will create a synchronous copy on another worker node. You can even specify REPL3, which will give you 3 copies. So yes, this will take up 3 times the storage on SSD. By the way, if you were to do this on a LUN that is backed by FlashArray would dedupe that back. So the 3 copies would be exactly the same. So a FlashArray would be able to dedupe it back. Obviously, if you use local storage, there's no dedupe. So you store 3 copies in this case. So what happens if a node fails? Well, we have this thing called Stork. And Stork is an extension to the Kubernetes scheduler that makes Kubernetes storage aware. So Stork knows where the copies are. So the moment that you fail a node, Stork will come in and say, hey, Kubernetes, if you're restarting this workload somewhere else, please prefer worker 2 or 3 because they have a local copy and they'll be faster. So probably Kubernetes will start it on the second worker node. So a question that we often get is what happens if for some reason the workload isn't allowed to start on worker 2 or 3? Well, then it may start on worker number 5 in this case. And because Portworx Enterprise is installed across all of the worker nodes, in this case, Portworx will still deliver storage to your workload. The only thing is it's not local in this case. So it will still work, but it will fetch the data from other workers. So where is this used? So imagine you have a public cloud environment and you want to burst at some point. So you have a Kubernetes cluster. At some point you need to burst, so you want to add workers. That is fine. If they're not storage nodes, you can just add them and remove them freely, right? So you can grow and shrink as you want. It's way harder to delete worker nodes because if you're deleting worker nodes, you're deleting storage. And at some point, you may actually delete enough storage to have it unavailable. So that's where we use this, these, as we call them, storage-less worker nodes. So architecturally, Portworx will talk among themselves using gossip, right? So they all be communicating. Usually in production, you have separate NIC for this in order to enable the east-west traffic, because also replication needs to take place through that, of course, right? If you have multiple copies, that needs to traverse. As you can see, we're still using CSI because in the end, that is the way that it communicates. And we use our own etcd, which is similar to Kubernetes, right? Kubernetes has 3 control plane nodes running etcd. We have what we call the key value database, which is also etcd. So it's, in that respect, completely similar to the way Kubernetes works. And we do that everywhere, right? We follow the way of Kubernetes. Right, very low infrastructure requirements. So the minimum is 4 cores, 4 gigs of memory. Recommended is 8 cores and 8 gigs. So usually you need to reserve some resources for Portworx to run, but it is very thin and very efficient. So you can just run it next to your worker nodes, right? So you don't need, so for an OpenShift, for example, you can have specific infra nodes that will do things like provide storage. For Portworx, that's not required. So usually we just install it with the worker nodes, and that makes it more or less an HCI-like approach. So now up into running virtual machines. There are some common problems with virtual machines. And of course, so these are some of them, right? You need mature, scalable storage. That's something that Portworx definitely provides. We can run it on top of any block storage. So in some cases, HCI with local disk maybe smarter. Sometimes we're backing it with a storage array, depending on the use case. But if you want like a no problem thing that scales out forever, then very often local disk is the answer. You need data management. So you need something that will easy to manage at scale, whether that's day 0, day 1, or day 2 data services. And we'll get into some of the features that Portworx provides to make this really easy. And finally, operational and scale challenges. Like I said, when you run CSI and you do a one-to-one mapping, at some point your array will probably run out, not in performance, not in capacity, but in the sheer number of LUNs that it needs to provide to the Kubernetes system or the Kubernetes clusters in order to have all of these PVs running in all of these LUNs. So that's, like I said, the abstraction layer that Portworx provides, right? We have a few big block devices that we into Portworx. Portworx creates a pool out of those, and then Portworx will take care of the scaling issue. So this delivers a highly performant scalable storage solution. To be honest, we are running directly in the Linux kernel. So when you install Portworx, you'll see containers sitting there, but the containers basically just manage the process, which is more or less similar to the way Kubefert runs VMs inside a Linux OS. It does allow us to be very lightweight and very powerful with low latency. We have features for disaster recovery. We'll cover that later. Backup and migration, same thing. And of course, we have a big ecosystem of partners. For example, Red Hat. We work a lot together with Red Hat because, well, I should say that most of the larger customers choose Red Hat OpenShift as the Kubernetes platform that they're using. And as a result, we came up with this. So from Portworx, we have special licenses. So the Portworx for Modern Vert licenses. They cost about half of a regular Portworx Enterprise license, plus they feature DR as well. Red Hat has a similar thing, the OpenShift virtualization engine, or OVE, which is a similar offering for when you're just running VMs on OpenShift. And that means you save a lot of money in licenses, actually even up to 85%. So when you compare the cost in licenses from VMware VCF9 compared to the Red Hat plus Portworx solution, you can have quite significant savings. So this is, again, this is an official slide. It's too many words, I think, but so cost avoidance, obviously. You have operational efficiency because you now have VMs and containers running hand in hand on the same platform. And you can run them anywhere. You can run it on-prem, public cloud, or you can even do hybrid. There's a very cool quote from the Chief Product Officer at Red Hat. Who says, well, we're pleased to collaborate with Portworx to bring the expertise and data management capabilities to Red Hat OpenShift. So basically, I would say it's the best of both worlds. Red Hat OpenShift virtualization engine for running your VMs and Portworx for storage. I'd like to translate the slide in this. It's 85% cheaper. It runs both old and new at the same time. It runs on any, so any infrastructure in any place. And it's just very, very cool together. So one final piece that can impact the way you do storage inside virtual machines especially is this, live migration. So when you look at VMware, they built this very smart thing called VMFS. So that's actually a multi-writer block system. And I think it may just be the only one that's really successful in the world that manages to do multi-writer for block. Within Kubernetes, that does not exist. So what you need is read-write many volumes. So you have volumes capable of being written to by more than one node at the same time. So we support that. We have our own trick to actually grab a block device and make that multi-writer capable. That's what we've got running in the lab at the moment. Since Portworx Enterprise 3.4, we also have the availability of raw block multi-writer directly. So that basically means that you surface up a disk device that is multi-writer capable directly from the underlying block storage. So live migration is cool, right? It is supported. It works really well. We'll be seeing that in the lab as well. But what if a node failed? Well, same thing as before. Stork will come in and say, hey, this node has a local copy, so please start it there. Again, if it can't, it could start on node 3, and then it will still work because Portworx would run across the entire set of worker nodes. So that will basically help. It will restart, reattach within a couple of minutes instead of multiple minutes. So it actually makes H8 failovers much more fluent. So this is the trick I was talking about. So before we had raw block, we would use this trick. What it does, it's called shared v4. And what it does, whenever you need a PV, it spawns a tiny NFS server next to the PV. And then all of the other nodes can use NFS to actually access the block volume underneath. So this is how we used to draw multi-writer storage from an underlying block device. Right, final bits and pieces before we dive into the lab. Autopilot. So Autopilot has some very cool capabilities. So this is basically what it does. So here we have Portworx. Portworx has provided with some storage, and by default, Portworx also installs Prometheus, where you can grab all of your metrics from. In OpenShift, it wouldn't install Prometheus. It would just use the Prometheus that's already part of OpenShift. But in the end, you'd have Prometheus. And yes, we also have Grafana dashboards standing by. So you could just plug in the pre-built Grafana dashboards and look at it. But what it also does, it also uses Prometheus to have this thing called the Autopilot Inference Engine. I should call it AI actually, because it seems pretty smart, but it's not so smart. It's not really AI because it's around this. It's about rule sets. So you can define rule sets. We'll be seeing that for the volume resize, by the way, in the lab as well. So you can resize volumes and you can say, hey, the condition for a PV or PVC or a group of PVCs, whenever the volume used capacity goes over 70%, please scale the volume by 100%. And by the way, you can also specify a maximum. So when a developer says, I would like to have a terabyte volume, you could give him a 250 gig volume and say, hey, make it auto grow using Autopilot, so we won't be consuming all of that storage before we actually need it. Maybe even cooler is that we can resize pools as well. So a pool, that is grabbing the storage from underneath and then build it out into a pool. So at some point, when you start carving out PVCs, at some point the pool will go full, and then we can do a pool resize for certain infrastructures, because obviously we need to talk down to the infrastructure to say, hey, get us more storage. So that's something that we call cloud drives. It's supported on a number of platforms, and it allows you to automatically grow a pool that the PVs can then use. And finally, we have a rebalance. So you can rebalance capacity in case it might go crooked. You can rebalance by building a rebalance rule. So basically, Autopilot will constantly measure the metrics, look at the volumes, look at their size, look at the amount of use, and at some point it might trigger and say, hey, this volume has, for example, gone over 70% of its capacity. Now I need to scale it by 100%. So it will go back and say, hey, please scale that, and that's it. So imagine, especially when you have this case, maybe doing a pool resize, this makes it particularly interesting. So in this case, I have like 2 volumes per worker, and I have a storage pool. So now if I were to drive that, I could do it like manually. I could say, hey, if you deploy a new worker node, you grow your cluster, please go down to the infrastructure and grab some new volumes for that worker node and the pool would grow. You can also drive it through autopilot. So if the storage pool is nearly full, Portworx could actually talk down to the infrastructure, and you can see what is supported. It's basically the three main cloud providers that we can talk to and say, hey, get me a new block device, mount that into the worker nodes, and the storage pool will grow. You can also do it for VMware. So in case you're running OpenShift on top of VMware, for example, you could do the same. Or if it's backed by a pure flash array. So we can talk down to the pure flash array and say, hey, carve out a new volume, surface it up into the worker node, or into a new worker node, or carve out a number of volumes, mount that into the worker nodes, and then automatically it will grow the storage pool. So this is interesting because it takes a lot of headaches away from managing the solution at scale. It also saves you a lot of cost, because imagine in public cloud, why would you give each worker 3 volumes if you're only using 2, right? You'd be paying too much money. So how easy would it be if you can say, hey, we're going to give them 2 volumes, and then when they fill up, we're going to automatically add volumes. So you only start to pay when you actually add them. But that can save a lot of money. Right, enough talk. Let's dive into the demo. Like it says here, what could possibly go wrong? Well, I know a couple of things, but we're gonna try and make it work anyway. There we go. So here we're looking at the lab, and it is an OpenShift setup. It has virtualization installed. Portworx is in there. Let's see. So it's a small environment. And it's really slow. Let's see if we have more success within the OpenShift console. Set compute nodes. This is very interesting. Okay. See if I can fix up another. Let's see if this works better. Because why would you have one lab if you could have? Right. Oh, at least this is responsive, so it might be good. Yeah, there we go. So you can see it's a tiny little lab. Just for a sec. I've got 1 control node, and then I have 3 worker nodes. We do have Portworx installed, so if we were to go, get me the pods from the namespace Portworx. See, yep, there's many stuff here. You can see autopilot is running in here. You can see some API that's basically just handing it through. We have the KVDB, which is our etcd, and then several other components. What's interesting? Well, the operator is running, obviously. And then here you can see we have Stork, which is the extension to the scheduler, basically making Kubernetes storage aware. Sure if this is implemented. Yes, it's here. So this basically tells me the status of Portworx. It's installed. You can see it running on all 3 nodes. They're online. And basically, we're good to go. It has seen the device is /dev/sdb in each of the worker nodes, and it's called that storage medium magnetic. It's not too fast, but so this demo is running on Google. So those are basically block cloud drives, if you will. So yeah, they might be a tad slower. What I also have installed is an application. which is called PX Barbecue, and that is our production application, if you will. So the funny thing is that you can see that this is a container, PX Barbecue Web, that's a container. But the other one, Virtual Launcher, MongoDB, this is a virtual machine. So in this application, we actually have a virtual machine and a container. They are seamlessly put together because they're using the same virtual network. So that works, that makes it easy. Also, so if I see, yeah, that is definitely a virtual machine running there. So we should be able to see that one in OpenShift as well. Just go there and see what's what. First, let's go take a look at the installed operators. So you can see we have OpenShift virtualization installed, and we have Portworx Enterprise installed. For the Portworx Enterprise piece, you can see in storage. Let's look at the storage classes. So lots of storage classes are defined by default by Portworx. So all of these you see here. So you can see that some can be replicated or non-replicated, encrypted, non-encrypted. If you want, you can delete all of those, right? They're put up there by default. So specifically for running virtual machines, we created this one, the VM storage. And this one actually, when we go into the YAML code, right, you can see that, for example, REPL equals 3. So as you can see, we're making 3 copies. Shared v4 is true. So this is an older setup of Portworx. So we don't have the raw block multi-writer capabilities here. So in this case, we're using shared v4. So that's the tiny NFS head that we deploy next to the pod, or sorry, next to the PV, actually, to make it multi-writer capable. So that is all in here. Look at persistent volume. Several. This one is interesting, right? Within Portworx Barbecue, we do have a 33 gig capacity drive here for MongoDB. And we're using 2.6. So this is important for the autopilot lab that we're running later. So what is running is our little PX Barbecue. Yep, you can see that there's this bound PV here. And when we look at virtualization, we should see a virtual machine. Here we have the virtual machine running. And also here you should be able to see the disk size. Yeah, there's our 33 or 32.61 gig. We can see what it's doing. We can get into the console. So this is basically fully YAML configured virtual machine. So it's all driven by YAML code. So similar to containers or VMs alike, you can just build this out and just deploy it and it will run. What is it actually running? Well, it's running PX Barbecue. It's failing. This is probably, now I need to show the instructions to the browser, and then hopefully, there we go. So this is our production application, right? Using MongoDB in the backend and using a container as the web front end. What we'll do first is, well, order some barbecue. So let's order some barbecue. First, log in. I'm a regular customer, so I already have an account. Right. An order. Again, for a main dish, let's do pork, I don't know, fries and pudding. As a drink, I have no idea what it is, but I definitely want the pork special. I'm going to place the order. Right. Order number 10,000. It should be in here. Look at order history. I can now see that, yes, there's been one order entered into the system that sits in MongoDB right now. And should be able to actually query that. So now I can query. Right. So here's my order. Right. The main order is pulled pork. So this is basically real-time pulling from the MongoDB database. So you can see the order ID is 10,000 and the main dish is pulled pork. If I were to add another one, of course, you'd see 2. Actually go for 2. Order some more. This time I'm going to have a brisket with French fries and baked beans. The cola. Place this order. Now, you can see I have 2 orders in the system. When I go back to the terminal, yep, it's been added. So now I see 2. Another interesting thing is that it also reports where the VMI is running. So where the virtual machine is running. And currently it's on node that starts with 9 PD. Right, you can see it's running here. So I could actually go back to the virtual machine and say migrate. It's migrating. Go back to the terminal. See, it's still running on 9 PD, but it's not really responsive, and that's because it is being moved. And as you can see, yeah, we lost one query, and now it's been moved to the other side, CZN. So that's another worker node within the cluster, and we just did well what VMware people will know as a vMotion, called live migration here. So we can just do live migrations, basically similar, losing a ping, right? Because if you move the node, all of a sudden the network moves, and now the network, whenever you do an inquiry, you will end up in the wrong node. The network will say, hey, where's this MAC address gone? And then the switch will say, oh, it's now on this server. So that's why you're losing one, and then it resumes. That's, by the way, completely similar to the way that you would see in VMware ESX as well. So what we've done basically is we have demonstrated the running application that has a virtual machine and a container, and they're working together. We've done a vMotion, or a live migration, as it's called, from one node to the other. You can probably tell I have a long history with VMware, so I just tend to call it vMotion. So the next thing that we could do would actually be scaling. I'm going to need the instructions here. Look at the auto scaling part, because it has some commands that I need to run. First, I need to clean up. So that will clean any stuff that I may have broken in the lab so far, and then I'm going to check for the next part. Yeah, and we're doing Portworx autopilot. Start this piece of the lab. Configure an autopilot rule. So this has all been pre-built, of course. Here you can see, so this is an actual autopilot rule, and we're going to name it volume resize. So remember, we had pools on like the south side of Portworx, volumes on top, right? Those are the actual PVs or PVCs. So we're going to resize a PVC here, and you guessed it right, it's going to be the MongoDB drive that we're going to extend. So we're going to do a volume resize. We're going to say auto expand is on for both namespace and labels. And this is the key. So here, this is a very fancy way of saying whenever the usage goes over 10%, 5 seconds, then we're going to scale with a percentage of 100 to a maximum of 75 gigs. So this rule will monitor the usage as soon as we go over 10%, which is very low. But of course, we don't want to wait for like 30 minutes because we need to fill the disk, and that takes time. So we set it to 10% to make it a bit quicker. And then it should grow the 33 gig device to like a 70-some gig. So let's apply this rule. So now we've got an autopilot rule. Now next we're going to set the labels. So we're going to label the MongoDB PVC to actually say auto expand equals on to make sure that it can expand. And we're going to do a similar thing for the namespace. Now we're going to extend the storage capacity. So here you can see the current size. Yeah, that's the 33 gig we already saw before. And we're going to start filling the disk. So we're going to run a process. This process will basically fill up the disk. Now we're going to run this query. So this will just be sitting here. So basically Autopilot has just kicked in. So Autopilot found its first rule, right? We just defined a rule. We put it to a namespace. We put it to a MongoDB PVC specifically. So now Autopilot springs to life and says, hey, I have a rule to monitor. So now it will set up monitoring using the Prometheus component that in this case sits inside OpenShift to actually monitor that disk and specifically its usage. Whenever it goes over 10%, it should automatically grow. So as this takes time, this would be a good point to jump back into the presentation and do some more presenting. And then we'll revisit after the second part of the presentation and we'll see what happened. So jumping back in the presentation and continuing with this thing called disaster recovery. So it would take too long to actually demo that in a lab. So that's why presenting around that now. We have two flavors of disaster recovery within Portworx, or I could actually say three, but the third one is not actually part of our DR, but it's the Kubernetes native way, and we'll be seeing that as well. So disaster recovery, sync and async. We're going to start off with async DR. So this is basically the cleanest way of doing DR. And why? Well, because it works like this. You have failure domain A that may be data center 1, for example. And then on the other side, we have failure domain B, which can be data center 2. There's an object store in between. We do need that object store because all of the changes that we make are actually stored in the object store. And then failure domain B will grab those changes constantly. So yes, it's asynchronous, but in order to perform a failover, you don't actually need the object store. So if you don't have access to an external object store, what we see customers do is that they'll install an object store like MinIO, for example, on the source cluster. It will use that to actually do all the migrations. And in case failure domain A goes away, meaning it has a failure, we don't need the S3 bucket anyway, because all of the data will be asynchronously replicated already here, ready to go. So this is basically the way it works. Through the object store, we are doing asynchronous replication of all of the PVs. So this is a Portworx cluster, or I should say this is a Kubernetes cluster with Portworx installed. So it builds a Portworx cluster. The second one also builds a separate Portworx cluster. We're doing async replication of all of the PVs. And we're doing asynchronous replication of all of the resources. So all of these, like the replication, the replica sets, the stateful sets, all of the relevant Kubernetes objects for an application get asynchronously replicated to the other side, and they're being scaled down to 0. So basically they are there, they are on standby, they don't consume any resources because they've all been scaled to 0. So Kubernetes just sits there and says, well, this is a replica set, but it's scaled down to 0, so I don't need to run any containers. We can do any distance or any latency because it's asynchronous. So you can do this from on-prem to public cloud, between public clouds, from Europe to US, maybe a bad example, from Europe to Canada, or anything. And that's the clean solution here. It is completely separated from each other. So very often we tend to protect against disasters, which often in our minds mean physical destruction, right? So what happens if data center 1 is hit by a meteorite? There's also this thing called logical failure. what if someone decided to wreck the etcd database for Kubernetes cluster 1? Your cluster would go down. Cool thing is, this is completely separated. So whatever issue you have in AZ1 or data center 1 won't have that issue in AZ2 because it's all separated. Downside is it's async replication. So it's 15 minutes or slower, which means that if you have a failure, you may lose up to 15 minutes of your data. So the thing fails, and Kubernetes cluster 2 is like with a one single command, you can scale the replicas up. So basically, all of these replicas that sit here, they have an annotation for the size that they used to be. So the moment you need to do a failover, we will look at the annotations and say, hey, Postgres, that had like a REPL factor of 1, so it needs to spawn, like scale it back up to 1. Kubernetes will notice the change and say, hey, this replica set or this stateful set now has a size of 1, so just build it up. So basically, it will recover within a minute. And then, of course, you need to add the time all of your applications will take to actually start, especially in the case of virtual machines that can take a while. And if you don't want to lose any data on failures, we have another solution, which we call synchronous or Metro DR. So Metro is slightly different. As you can see, we still have separate Kubernetes clusters, but we have one stretched Portworx cluster. So the Portworx storage cluster gets stretched across 2 data centers or 2 failure domains, basically. And then if you deploy a workload with REPL 2, so that's the only one supported in this scenario, Portworx, or actually Stork, will make sure that it says, hey, this Portworx cluster has 2 failure domains, and we have 2 copies for our data, REPL equals 2. So now I need to make sure that one copy always sits in failure domain A, the other copy sits always in failure domain B. So that's the way we construct Metro. So now anything you deploy on cluster A, for example, will have a copy of the data on one of the worker nodes here and on one of the worker nodes there. Obviously, Stork will try to match those and say, hey, please start it on worker node number 2, for example, because we have a local copy there. But that's more of the same, right? For Portworx, it's just one cluster at this point. Another thing is we need to have an external KVDB at this point. So you need to install a separate etcd instance. That can just be a Linux VM that basically runs Podman or Docker container. And we also have this thing called a witness, because, well, if everything works in the Kubernetes way, and so does Portworx, that means we always follow majority of nodes. We have 3 worker nodes and 3 worker nodes and 2 copies of the data. If you lost a copy of the data, you'd lose majority, so you lose access. So that's why we have a witness there, in order to make sure that majority of nodes will continue to function. So this is another view of the same thing. Again, so we have one stretched Portworx cluster sitting underneath. That will replicate synchronously your data, so it needs to be within 10 milliseconds. So that's a general rule for a Portworx cluster. All of the worker nodes need to be within 10 milliseconds of each other. And the resource migration is similar to the async one. So this is asynchronous, which kind of makes sense, right? Because if I create a new application, I wouldn't want to wait until there's like replica scale to 0 down here before I acknowledge it back. So you can just deploy an application here, and then asynchronously, we will replicate that or those Kubernetes objects to the other side, scale to 0, and then you'll be protected. All of the data is always synchronous. So in this case, as you can see, it is a less cleaner version of DR, because where asynchronous DR had everything separated, literally everything, right? There was just an object store in between that would write and we would read. They would be completely separate. So here you're seeing that we have one Portworx cluster. So break the Portworx cluster, break both sides at the same time. So this is a risk. That's something that you need to need to take measures for. But it is the way of making sure that you never lose data, because this is synchronous. So any write that occurs here will synchronously traverse to the second copy and be acknowledged. It will need to acknowledge back before we actually continue. So that, by the way, is also why you never want to go over 10 milliseconds latency, because each write will always traverse the WAN and the acknowledgement back. So the round trip time is actually the latency that you incur on any write. By the way, that's similar to any synchronous replication or active metro-like situation, right? It's the speed of light thing. We haven't solved it yet. So again, if Kubernetes cluster 1 failed, there would be like a single command with 0 data loss to actually scale your application back up on the remaining sites, and things will recover. So those are basically the 2 ways Portworx can help you with doing DR. That said, it is more or less like the old approach. So in the old days, we used to have like dual data centers, or maybe active, maybe replicated between the 2, but you'd have an active and a standby. So, and we basically, Portworx DR actually feeds directly into that idea, right? You have one availability zone and the other availability zone. Now we do replication between those. And by the way, we can also do like 50-50, so 2 ways if you want to. You could also look at the way Kubernetes solves things. In that case, you wouldn't even need DR. You could have 3 data centers. And again, you'd have to have 3 data centers, all within a 10 millisecond range. Then you could build a single cluster that runs in 3 availability zones, meaning there are 3 data centers, meaning there's a control plane in each data center, and then there's workers in each data center. You can have block storage in each data center, and then you could add a single 3AC Portworx cluster on top of it. By the way, we also have etcd in 3s. So we would also deploy in each availability zone 1 etcd node. So similar to the control planes. The majority is always maintained because everything is in 3s here. So lose a data center, well, lose 1 instance or lose 1 control plane node, lose 1 of our KVDBs, lose 1 copy of your REPL3 dataset, but you'd always have majority left, which means the cluster would always survive a data center failure in this case. So this is a way you could actually build a DR-like thing without actually calling it DR. It's the Kubernetes way of doing things. Still, we see a lot of customers going back to the DR solution. Why? Usually because they only have 2 data centers. Maybe a 3rd tiny one where they run witnesses, but that's very often not a full-fledged data center. So depending on what you have and what you need, you may have to change these things. Right. We're on trucking. So what if you don't want to fail over, but you logically broke something and you need to go back? That is where snapshots can come in handy. Snapshots are part of the CSI driver specification. So most CSI vendors, if not all, will support creating snapshots using CSI. That said, it's really cool when you can make a snapshot, but what happens if your SQL instance has multiple devices attached, multiple PVs attached, or any application? So if you want to snapshot an application, you need to snapshot everything at the exact same time. So this is where Portworx can help as well. First of all, we have like volume snapshots. So that's just a snapshot that is a point-in-time clone of a volume. We are using copy on write, which means creation of a snapshot is instantaneous and it won't take up any storage until you start doing more writes, of course, because now we got to maintain like 2 points in time that are current. So that means that, yes, the data will start growing, but initially it's fast creation and there's minimum overhead. You can also schedule snapshots. So within the storage class, you can define and say, hey, I want you to create a snapshot like every hour and keep 5 of them. What we also have are what we call volume cloud snapshots. Same thing, but an entire volume backup gets now stored in a remote object store. Well, actually, either an S3 compatible object store or an NFS mount. So this allows us to basically back up a volume in an object store. Now you can see how this might segue into a backup solution later, right? It's one of the many features. Because we're in the data plane anyway, we have a very easy way of actually orchestrating backup and restore, but we'll see that later. What we also have are application consistent snapshots. So if you take a snapshot, if you have a running application and you just take a snapshot, we call it crash consistent, because the state of the disk at that point is as if the application crashed, right? It just stops at some point because we took the snapshot. Better way of doing it is talking to the application and saying, hey, please flush all your stuff to disk and go to sleep while we take the snapshot and then you resume. That is a fully application consistent snapshot, which we can also do. So whenever you take a snapshot, we can do pre and post commands before and after the snapshot, and actually to quiesce databases and make sure that it's all consistent the moment we take the snapshot. Right. Looks something like this. So you see an example for Cassandra where we have a rule it's like a pre-snap rule, and basically what it says, it's a command, and the command is no tool flush. So flush everything to disk, then we take the snapshot. So that's an example of an application consistent snap that we're making. And finally, of course, like I said, what if your application has multiple PVCs? You want to snapshot them all at the exact same time, and those are called volume group snapshots. So you can actually build a group of PVCs and say, this is a group, snapshot the entire group. So this all segues into this thing called backup. So when we go back to the world of VMs, it's relatively easy to take a backup of a VM, because in the end, a VM is just a bunch of files, right? It's a boot drive, it's a config file, and basically when you grab everything, you have the entire virtual machine. Now you're running VMs inside Kubernetes. Now all of a sudden, you have PVCs, so virtual disks. You have etcd configuration. You have stuff sitting in controller and worker nodes. You've got all kinds of Kubernetes objects. If you want to back up a virtual machine that lives inside Kubernetes, you need to grab all of these things and be able to restore all of these things in order to back up and restore a virtual machine. So this is where Portworx backup comes in. And this is an older video that you're seeing here, but it does really well show what it's actually doing. Because we've been discussing things like snapshots, cloud snapshots. We have PX migrate, which I haven't really covered, but that's a way of actually moving Kubernetes objects between namespaces, between clusters, or into S3 object stores. So Portworx backup is more or less just a control plane tool that will talk to our data plane and say, hey, please move this PVC as a cloud snapshot into S3. Hey, PX migrate, please grab these Kubernetes objects and move them into the S3 object store. So Portworx backup sits on the sideline, talks down to various components, that is like PX store, Stork, in order to basically tell the data plane what to do. And that's how we do backup and restores. So if you add some smart things like it, like the way that we have robust access control and multi-tenancy, it makes it really powerful. We've even got customers that, for example, a developer sees an issue in an application, takes a backup, goes into the GUI for Portworx backup, shares that backup with a colleague and says, hey, please look at this backup. So he restores the backup in a different namespace, maybe using a different source class, can actually see whether there's something that he needs to fix there. So it also enables cooperation between DevOps teams. And of course, it allows you to do backup and restore. We can even do it in immutable S3 backends. which now means that it's sitting there, it's encrypted, it's impossible to delete. So for ransomware protection, you can always restore. Right, as we're running out of time, I have some more Portworx features that I don't have slides on, but I just want to mention them quickly. Cloud drives, we actually covered. So cloud drives, right, the way that we, for Portworx, can talk down to certain types of infrastructure to automatically either grow or get more volumes in order to grow a pool within Portworx automatically, whether that's because you have added new worker nodes to your cluster, and now you want automatically storage to be surfaced underneath those new worker nodes in order to grow the pool, or maybe it's autopilot driven. Cloud drives enables that automatically from like the underlying infrastructure. Multi-tenancy and role-based access, I quickly touched upon those. Yeah, it isolates users and teams. So similarly to Kubernetes, which is like multi-tenant, we just, well, work the same way, right? So we can also do multi-tenancy, role-based access control, which means developers can only see what they created themselves as a team, other teams did, like that. Role-based access basically integrates with Kubernetes as well. So that goes into Portworx itself, but also extends to things like backup, where, like I said, where you're like sharing a backup. Basically, that is giving a role to a backup to another DevOps and say, hey, you can view it, you can restore it maybe, or you can administrate it, meaning delete it as well. So that kind of role-based access is also there. And finally, encryption. So within the Portworx Enterprise platform, we can do encryption. So encryption actually takes place inside the Kubernetes layer itself, so within Portworx, which means anything going down to any block device can also be encrypted. And finally, really interesting, often forgotten, we have a trash can. So you can configure a trash can. If a developer says, delete this PV, and then he goes like, oops, I shouldn't have deleted that PV, you can actually go down into Portworx. And if you configure the trash can, of course, it will still be there. It will be sitting there for a number of days that you configure in the trash can, and you can actually recover that volume, return that into the world of Kubernetes, and then the developer can have his PV back. And of course, mount it as a PVC again. Right, final bits. Let's look at the lab. Where did we get to? I need to, there we go. You can see a lot of stuff happened. It was initializing, then it went to normal state. Then it seems to have skipped. Wait, I really need to restart this. Yep. Normal, normal. Yeah, it has done, I think it has done multiple instances actually. So it got triggered, then it said it has active action pending in progress, and then actions were taken. So you can see that autopilot was sitting there normal, then it triggered at some point, and it actually, so it put in some actions and said they were pending, they were in progress, and then actions were actually taken. So if I look, well, I can look here. If I say get me the PVC for the namespace BX barbecue, yep, I can now see that storage capacity has doubled. So it's twice as big. And without any hands-on, I should be able to see that here as well, right? If I look at the VM here, yeah, there we go. So fully automatic, it has like scaled, in this case, the volume. You can imagine, right? It can do the same thing with the pool. So if I were to create more virtual machines, and I would be carving constantly out of the pool, and Portworx would run out of pool space, we could actually talk down. So in this case, this runs on Google. We could go down to Google and say, hey, get me a new block device, mount it into these worker nodes, and grow the pool for me. So that is basically all I have today. So up next is answers. So were any questions posted in the chat or? Hey?
Sorry, I just needed to unmute Eric.
No
yeah, quite early on, there was a couple of questions. One was pertaining say, yeah, the question is more like, our operations team are, obviously very comfortable using VMware related tools such as vSphere and so on.
Yeah.
Running VMs in KubeVirt, as an example, introduces new abstractions, failure modes, debugging paths, and so on. And the question is really, is there any support available to do a migration over this way of doing things, in a safe manner?
Yeah. Well, basically that it's officially that's not my role, right? I just deliver storage. But so when you look at Red Hat OpenShift, I would say that OpenShift has the most mature platform today to run KubeVirt in like a fully in a full ecosystem. And they've also extended this. So what they can actually do, they can come in and look at your current estate of virtual machines, and then they can actually group them and say, hey, these are easy to migrate. These are a little bit harder. These may be impossible to migrate because, well, to be honest, there is no exact feature parity, right? So if, for example, it's not something that many people run, but let's say you are running fault tolerance virtual machines within ESX, really cool. CPU lockstepped 2 instances of a VM. When you kill one VM, it will just continue running on the other side without missing a beat. Really cool feature, but you can't support it in KubeVirt. So they will look at the entire VM estate and say, okay, so this one you can do. These ones will be hard probably because it might have some features that we solve in a different way. And then there's usually like 80% that is like the low-hanging fruit that's really easy. They actually provide a tool to help you migrate those workloads from an ESX platform into Red Hat virtualization. So they can help you there.
Okay, good. See here, I need to scroll a little bit.
Yeah, other questions might have been answered later on. As we
yeah, that's what I'm trying to sift through a little bit here. But another one is touching upon, say, we're an organization heavily invested in NetApp and Trident as a platform. They've seen some limitations with regards to backup capacity management and probably other things as well, potentially. And they've also in a situation where decisions have been made to move into a hybrid cloud strategy and so on. And how could Portworx help us navigating through these concerns or problems, if you will?
So when you talk about migration, so we have PX migrate, like I mentioned, we have PX backup. Basically what you're talking about, if you want to move from a CSI provider to Portworx, basically what all you need to do is move your data from one to the other. And then you can even have within the one cluster, you could have CSI drivers from one vendor, CSI from the second, and CSI from the Portworx enterprise, and they would all live as storage classes next to each other. So within once you install Portworx, it's radically simple to either manually from the command line, you could actually say, you could call upon PX migrate and say, hey, grab the application that runs in this namespace, move it to another namespace, and as you're moving it, please move it to the other this other storage class. If you don't want to do that manually, you could use PX backup and say, hey, draw a backup, pull it out of this namespace, pull it out of this storage class, and then restore it back into this other namespace, or potentially even the same, but usually you use a new namespace and this particular storage class. So you can actually migrate things between storage classes, between namespaces, or even between clusters if you wanted to, right? If you're like, oh, I don't want to, so this is my production cluster, I don't want to install Portworx there, but I'd rather build like a second cluster, have Portworx there, and then you can take the backup from one cluster, restore it to the other, and then just move stuff over.
Okay, yeah. Let's see here. I actually have a question from a colleague of mine. Might be a bit nasty, but I'll I'll give it to you anyway. So
I love nasty questions.
Yeah. So do you feel that Portworx in combination with containers and KubeVirt are mature enough for most companies to migrate from traditional virtualized environments?
So I used to think not a while back, but developments have been crazy, right? So mostly I would say it is a feature parity thing. So KubeVirt has been around for a long time. It is very mature, right? I think it was built in 2007 for the first instance. So it's not like a new thing, right? It's been there for many years. And basically it runs a virtual machine. So a virtual machine running in Linux, it's just a process that runs on the operating system directly. And then you take a container to actually encapsulate that process and manage that process in a Kubernetes way. But in the end, it is just a process that runs directly onto Linux. So it's scalable, it's fast, it's got most of the features that you need. So I mentioned the fault tolerance thing. They don't have that. So KubeVirt cannot do that. Is that important? I think I've seen only one customer ever that actually ran fault tolerance in production. They were this military customer. They had like 2 bunkers with like 10 meters of concrete, lots of networking in between, and they'd run fault tolerance virtual machines on both sides of the wall. But that's a really, really corner case. So if you're saying we don't have fault tolerance, 99.9% of the customers will go, we don't care.
Yeah, and you don't foresee any other specific corner cases that could be?
Well, there are different features that are actually not corner cases. DRS is a very good example, right? VMware for years have had the ability, so they're measuring resources that are being used between the nodes, and when they see an imbalance, they'll just move virtual machines, and that will balance the load automatically. So with DRS enabled, motions or live migrations are taking place all day long, and constantly they will be making sure that all of the nodes are loaded more or less equally. That is actually a feature that everyone uses, and it's not there today. So that can be a reason that you're saying, maybe not, right?
Yeah.
Or maybe just some of the low-hanging fruit that we're moving over. But of course, those features will come, right? Storage DRS, similar thing. Storage vMotion, capability of moving a virtual disk under a running virtual machine. Didn't used to be there. Now it's in tech preview for OpenShift. Next, I'm guessing that the next release of OpenShift virtualization, it will be G8. So these features are coming rapidly, and I have seen customers that migrated 30,000 virtual machines onto OpenShift. And that, for me, that was like the pointer. I was like, yeah, these guys just were doing something, right? They were just like, oh, let's migrate 30,000 virtual machines. But no, right? That's not the way it works. They did proper testing. They did failure testing. They did everything before they were like, yes, we can move these virtual machines. To be honest, there's still like 6,000 they cannot move, but they have saved like 80% of the workloads, have moved to a 85% cheaper platform, equals lots of savings. So that's the way it is now. And by the way, by the time that they're done migrating their 30,000 virtual machines, new features have arisen. So they're going back, looking at the remaining 20% and saying, okay, so now we can migrate maybe 10% of those. And that's the way they will continue in the next few years. KubeVirt is developing more and more. So yeah.
Okay. Yeah.
I would say it's getting good enough. Definitely.
Okay. Yeah. I mean, that's everything I've gathered at least. So
okay. And
potentially we get 5
left,
minutes back. Yeah. Yeah.
Good timing. Okay. So if there's any last second questions, please post them now. Otherwise, I guess we'll be closing.
Yeah, that is officially a wrap. Thank you very much, Eric, for taking us through this demo session. Much appreciated. And
hey, you're welcome.
Anyone who joined who has questions they would like to handle offline with us and not in front of everyone, obviously just reach out to myself or Eric. You can probably find the contact details in the landing page on our website. So just reach out and we can address that in a separate session if needed and wanted.
Definitely.
Okay. Thanks a lot.
Sure. Bye-bye.
Bye-bye.